So in part B of question 2, we're given a solid plastic cylinder floating on water over here, and we're supported by a beam, AB. The beam has a length of 6 meters, the weight is 1,700 newtons, and we're given that the beam is uniform. That means that we can take the weight of the beam to be acting in the center of mass of the rod. So this is 1,700 newtons. The cylinder is floating vertically in the water. The top cylinder is attached to its center of the beam, distance of 5 meters from A, and we're applying a upwards force of 1,300 newtons. So this is the force from the block on the beam. A person of weight 660 newtons stands on the beam at point P. The beam is in equilibrium. We need to take moments about A to determine the x from A to P. So we're also given that the person is 660 newtons. So since we're in equilibrium here, that will mean that the net torque is going to be 0 on A. So all we have to do is consider these free forces and write their torque about point A. As you can see, these two forces will rotate clockwise. This single force will rotate anti-clockwise. So their torques must be equivalent. So the arm of the weight of the person is going to be this distance x. So that's the perpendicular distance between the line of action of the force and the rotational axis. So that will be x. And then we add the rotating force of the weight of the beam, which has a arm of 3 meters. So that's going to be exactly at the midpoint of the rod, right? So half of 6 is 3, and is equal to 1,300 times 5, as this has a distance of 5 meters. And then we just have to solve for x, and then we get that x is 2.12 meters. So we can just write 2.12. Okay, and then part 2, we're given that the bottom of the cylinder is submerged in the water to a depth y, as shown in this figure, and the cylinder has a mass of 11 kilograms, and we're given its diameter d. The beam exerts a vertical force, as we shown here, yes. Show that the up thrust must be 1,400 newtons. So here we just have to consider the equilibrium of forces. The sum of all forces must be 0, as the cylinder itself is at rest. So if we write the sum of y component of the forces, sum of Fy, we have this force acting downwards. This will be a minus 1,300. And we also have its weight acting downwards. So that will be another minus. And the weight is 11 times 9.81. And to this we have to add the up thrust. So that will be some force pushing it upwards to keep it in balance. And this must be equal to 0. So if we add them and bring them to the other side, we will get 1,408 newtons. Indeed, approximately 1,400 newtons. We're given now the water has a density of this, so we need to calculate y. So we have to recognize that the up thrust comes from the buoyant force. It's the force due to the fact that we are displacing a given volume of water. And so the up thrust is going to be equal to the weight of the displaced water, basically. So that's just going to be the density of water times the volume that we displace, times g. This is basically the mass of the water that we're displacing, right? Then we multiply it by g, and so we just get the weight of the water that we displace. So this is 990. Now the volume that we displace is just the base area times the height. That's the volume of the cylinder. This is going to be d squared pi over 4 times y, and then we multiply. This is a y. We multiply with 9.81. We know the diameter is 0.78. So we also know that the up thrust is 1,400. So all we have to do here is basically rearrange for y, and if we do that, we get 0.302 meters, just like this. Okay. Now we're told that the person can stand anywhere between A and B. On this figure, we need to sketch the variation of the depth of the bottom of the cylinder with the distance of the person from A, where distances between 0 and 6 meters, numerical values are not required. So we are required to sketch the depth of the bottom of the cylinder with the distance of person from A. Okay. So if the person is at A, there's still going to be some force that's still going to be submerged by some non-zero amount, firstly due to its own weight, but also due to the weight of the beam. So it's definitely not going to start with 0. And what we've also seen here is that the upthrust is basically proportional to this distance, right? So we have this upthrust and it's proportional to this distance y. So as the person is going to move to the right, the upthrust will have to increase because this is the only force that provides a torque counterclockwise. And since the arm of this force is going to increase as the person gets more to the right, the overall torque this force will have to provide is going to have to increase. And the only way that's possible is if the force itself increases. And if the force increases, then this displacement will also increase. So we're expecting a linear relationship. And as we said, at 0 distance, we're going to have some non-zero depth because of its own weight and the weight of the beam. And it's going to be some linear relationship because of the equation that we have discussed. And that was question 2.